Welcome to GHIST, the Genomic History Inference Strategies Tournament. I'm your host, Ryan Gutenkunst, coming to you from the University of Arizona. And I'd like to start by thanking the National Institutes of Health for funding my group and thus this tournament. I think we have the opportunity to learn a lot for the population genomics community and to provide a forum where people can test their skills and develop their skills in data analysis. So our agenda today is that first I want to introduce you to the competition and the motivation, and then I'll introduce you to the platform Synapse that we're using to host the competition. And lastly, you'll get to make your first submission using dadi-cli, an inference tool that my group develops, hosted on a cloud environment so that you can do it all from your web browser. So what is the problem that we're trying to solve? We're interested in population genomic inference. We want to learn some aspects of evolutionary history from patterns of genetic variation. And this is a problem very much like the blind men who encounter an elephant. You're probably familiar with this classic parable where, say, one of the blind men grabs the elephant by the tail and he says, "Oh, the elephant is like a rope." And then another of the blind men grabs the elephant by the tusk and says, "Oh, the elephant is like a spear." And all these blind men have different perspectives on what the elephant is, and no one can see the truth. In genomic data, in analyzing genomic data, we face a similar problem because we don't have any methods that can take in all the information that's available in DNA sequence data. For example, in my group, we're very interested in learning from data summarized in the form of a site frequency spectrum. You might also apply methods that rely on pairwise coalescent times, or that rely on distributions of IBD track lengths. And even the most cutting-edge machine learning methods that are trying to identify their own statistical summaries from the data, they're black boxes, and they're probably not maximizing the information we can extract at this point. So all methods are imperfect, and we also have different questions we want to ask. And in addition, we face many challenges when analyzing our data that our real data violates assumptions that are in the models that our tools are using. We may not have perfect SNP calls. We may be misidentifying ancestral states. We may need to phase the data. We might have polyploid populations. There might be selection acting either as background selection or hitchhiking. Genomic data is really complex. Our tools are relatively simple and imperfect. So the question then is, how do we know which approaches to use and when we can trust them and when we can't? Now, as a methods developer myself, I know that in my group, whenever we're developing some new approach, we try and stress test it. The challenge is that we're biased. Even if we try and do our best to be consciously avoid our biases, we're interested in certain problems and certain limitations. And frankly, when we're doing our tests, we know the answer we're looking for. So even as we try to do the best we can, any performance evaluation that we publish about one of our own methods has to be taken with a grain of salt. And that's true for everyone in the field. So how can we try and avoid these biases in the performance evaluations that we have? Well, one solution is to hide the truth from the people doing the testing. That if someone is going in blind, then we avoid a lot of the issues of tweaking methods to be perfectly suited to the test data. And if we open it up to the community, we also can see how do methods perform when they're being used by someone who's not the actual developer, but someone who has to learn from manuals and documentation and thus might not be using everything in the perfectly optimized fashion. And I am very heavily inspired by the critical assessment of structure prediction, CASP, which you may have heard of. This is a long-running project where every 2 years, the protein structure community has withheld certain structures that have recently been solved and asked people to predict, using whatever computational method they like, the folded protein structure from just the bare sequence. And as you'll see from this graph, over the years of the competition, there's been more and more progress in solving more and more difficult structures to high accuracy, as indicated by the y-axis. If you've been following this field at all, you may recognize that there was a big jump in the last competition. That was AlphaFold 2, which has revolutionized the field. Now, I don't think GIST is going to give us an AlphaFold equivalent in our first year, but I think we can make really interesting progress in learning what methods are best in population genomics. So I want to thank the people who have been helping me with this project. We have a design committee consisting of Peter Ralph, Katie Lauderhouse, Adam Siepel, and Andreas Moreno Estrada, who have given really insightful advice about how to structure a competition in a way that is really inviting and that we can learn a lot from. And for my own group, I'd like to thank Travis Struck, who is a research scientist who has really led the development of the whole framework we're using and the competition itself, built on the platform that Sage BioNetworks provides. So what does this year's competition look like? So we have 4 challenges of varying difficulty. We have an easy introduction, which we'll work through actually during this presentation, and then 3 more of what we think are roughly increasing difficulty. For this first year, our focus is on inferring aspects of demographic history. This is partially due to my own bias, in that my group has done a lot of work in this area. It's also maybe one of the most fundamental and simple population genetic inference tasks. And I'm looking forward in the future broadening our horizons to think about inferring selection or recombination rates or anything we can think of. Now, one of the biggest pieces of advice I got from the design committee is that for the first year, we want to keep things as simple as possible. And so we're going to be providing you error-free data in the form of a VCF file. And this is simulated data, because in population genetics, unfortunately, we lack golden ground truth data sets. We don't know the exact history of any particular group of populations. Instead, what we can do is simulate what we think are relatively realistic data sets. Now, this first year, we're toning down the realism and giving you error-free data so that we can have a real baseline to start adding complexity in future years. So what will you do in the competition? Well, we're going to ask you to infer certain aspects of the history, the time when 2 populations split, the magnitude of a bottleneck. So you'll have to, for each inference, provide a few different numbers. And then our scoring is based on the root mean squared error between what you submitted and the truth that we simulated. So again, it's a fairly simple evaluation metric, and we're trying to be simple and transparent. When you make your submission, we'll also ask you to submit a brief write-up of the procedures you used and what tools you used, how you approached analyzing the data. And this is really critical because this is where we're going to learn as a community. What methods did really well and what methods didn't perform as well. As a bit of incentive, the top competitors will be invited to be co-authors on the paper describing the competition. And submissions will be due October 18th, 2024. So that's quite a ways from the date I'm recording here. And that's really deliberate, that we want to give you a lot of time to work on this competition. And in particular, we want to encourage new students to join the competition. So new students who might be rotating in a research group, or new undergrads who are starting their first research in the fall. This challenge, I think, is a really great opportunity to say, if you're a mentor, here's a great data set to warm up and try doing some analysis in a really safe, open environment. So let's get cracking. The homepage for the competition is really easy to remember. It's ghi.st, and we'll jump to that and start exploring the competition itself and our competition platform. So now let's explore the Synapse platform we'll be using to host the competition. So the easiest way to get there is to go to the easy URL ghi.st, which will send you to a page on my group's website with a little bit more information about the tournament. But most important for us is this link right in the middle that will take us to Synapse. So if we follow that link, you'll see that it asks you to sign in. So unfortunately, you will need to create an account to be able to see any of the details about the competition itself. So the easiest way to sign in is probably to create an account is to link your existing Google account to Synapse or an existing OrcID account. But what I'm going to do is I'm going to create a new account using an email address because I want to create a fresh account that hasn't already been set up at all with Synapse. So we're going to take a slight break while I get my email checked to validate the account. And when I click the link to verify my email address in the email I was taken to this page where first I need to choose a username. And I can optionally enter a first and last name, and then I have to choose a password. Now I'm not going to use the password Google suggests because y'all saw it. So now my account is created, and I have to agree to some terms of use for Synapse. I have to treat people with respect and inclusion. I'm going to follow the appropriate rules. I'm going to act ethically. I'll keep the data secure and private. We're big supporters of open access. I'm going to give credit to people. I'm not going to do marketing or advertising. And I will report any suspected data breaches. And now I can go back to Synapse. So this sent us back to the main Synapse homepage. What we probably want to do is go back and follow that link to join the competition. And I'm still logged in, and now you can see the competition wiki on Synapse. Let's close this out. And you can see the layout of the page here that has some information about the timeline, our design committee, funding, a little bit of information. The first thing I'm going to do is click here to register for the competition. And so I can participate anonymously if I wanted to change my username and sort of clear out my profile. I'm not going to worry about doing that. So I will just continue. And I'm now registered for the challenge. That was pretty easy. So if we follow the navigation here on the left, under challenges, we can see the 4 tasks that are set out before you. So our introductory challenge is the GHIST-bottleneck challenge. So as always, we're going to provide you a VCF file with genomic data. And in this case, we have a population that has undergone sort of some population decline. And what we asked you to do is to infer the timing of that decline and the magnitude of that decline. And what you'll see is that the data we provide are the VCF file, and there's a YAML file that we asked you to fill in. So the VCF file in this case is not too big, a few megabytes. And the YAML file is just a simple text file to fill in the blank here. And so we'll go through this in more detail later, but all you'll need to do is change the T and the new here with whatever your inferences are about the timing and magnitude of that bottleneck. If we go back, we can look at the other challenges. The next level of difficulty is a multi-population challenge, where we have two populations that have split with isolation, and we're asking you to estimate the timing of that split and the current population sizes. For a more complex challenge, we have a scenario where there's been secondary contact in gene flow between some split populations, and we want to learn the details of that. And lastly, we have an archaic admixture challenge, where we'll ask you to identify the timing and the source populations that contributed to archaic admixture in the contemporary populations. So, under how to participate, we have some guidelines for how to make the submissions and how to get started in the challenge. So if you have any questions that aren't addressed by this workshop, you'll be able to get them there, get them answered there. We also have a news and updates tab, and the discussion forum here is pretty important. This is an opportunity for you to ask questions of us and give feedback where everyone will be able to see it. So if you have questions about the tournament that aren't specific to the details of your exact submission, I hope you will send them here so that everyone can see. If we go back to the wiki, we also have some rules and resources. Again, encouraging you to use the discussion forum to ask questions so that everyone can see what's being said. So I want to go back to how to participate, because one important thing you'll need to do is you're going to be submitting a file to Synapse to make your submission. And an important thing for Synapse to maintain their own security is that you follow the rules. And so you'll need to become a certified Synapse user. It's a pretty easy process, but it is one additional step. So you'll see that here that you must become a certified user. So let's become certified now. And to get certified, we'll have to answer this 15-question quiz about the rules of data uploading and data management on Synapse. Now, the quiz is different for everyone, so I can't give you the answer. The useful thing, though, is that for every question, there's a link with how to get help answering that question that will take you right to their policies. So the quiz shouldn't be difficult to pass. In the interest of time, I'm going to shut down this video while I complete the quiz, and then we'll return and work on creating our own first submission to the challenge.
A few moments later.
Hey, look at that. I nailed it with a perfect score. So now that I've passed the quiz, I'll be able to upload files and actually submit to the challenge. So let's go back to the GIST homepage. And our next step is to actually create a submission, get some data. And for this workshop, what I've done is created a cloud instance where I've pre-installed some of the software we might use to do some inferences. And so that is in Posit Cloud. So we can go to the front page of the Synapse site and scroll to the bottom and access our Posit Cloud workspace. And so this will be another account that we have to set up. Again, we can sign up with Google, link your existing Google account or GitHub or Clever. To make things as authentic as possible, I'm going to create a new account with that starts from scratch. And I sign up, and I will need to verify my email address. So we will have yet another quick break. Hey, look at that. I nailed it with a perfect score. So now that I've passed the quiz, I'll be able to upload files and actually submit to the challenge. So let's go back to the GIST homepage. And our next step is to actually create a submission, get some data. And for this workshop, what I've done is created a cloud instance where I've pre-installed some of the software we might use to do some inferences. And so that is in Posit Cloud. So we can go to the front page of the Synapse site and scroll to the bottom and access our Posit Cloud workspace. And so this will be another account that we have to set up. Again, we can sign up with Google, link your existing Google account or GitHub or Clever. To make things as authentic as possible, I'm going to create a new account with that starts from scratch. And I sign up, and I will need to verify my email address. So we will have yet another quick break. So I clicked on my verification email, and it brought me to this page showing me that yes, I verified my email. And I can go back and continue my login. And it'll ask me whether I want to join the space. So what I've done is I've created a space for our workshop, and by joining that space, you'll have access to that space. So welcome to GIST. And we can go up to content, and we can see there is a project called GIST Kickoff. And if I click on that link, it'll start the project. So this is firing up a cloud instance that already has some of the software we'll need installed. And it'll take a few seconds to deploy the project because, like I said, it's firing up a cloud instance. The expenses for the computing time and that you use while you explore this workshop will be billed to my grant eventually. So I ask you to please not be too excessive. The goal here is to do some quick analysis and really explore what we can do as part of the competition. We are almost there. And so Posit Cloud is built around RStudio, which many of you are probably familiar with. We're actually cheating a slight little bit here in that the main feature we're going to be using of RStudio is the access to a terminal where I've installed some software that will be useful that is command line. And so to set up our paths, the first thing we'll do is source activate.sh. That just sets up the paths so you have access to the software I installed. So if we go back to our Synapse page, we're going to be working on the first challenge. And we can follow the link to our VCF file and easily download the file. And you'll see I've downloaded it before. And in fact, that's the exact same file that I've already uploaded to the workspace, just in case there were any internet connection issues when I was doing this live. So I want to pause for a second and switch to talking about the tool we'll be using, which is dadi-cli. So today we'll be working with dadi-cli, which is an inference tool my group has recently developed based on the venerable population genetic software dadi. So dadi-cli is a command line interface to dadi, which is a Python package that has been serving the community well for many years. Dadi-cli is available on GitHub, and you can also install it from CondaForge. And just like dadi-cli enables us to fit population genomic models to allele frequency spectra. So dadi-cli is built on a number of subcommands that allow you to perform all the steps of the potential analysis. So you start with the VCF file from which you might want to generate a frequency spectrum. From that, you could infer a demographic model. You can analyze the best fit sets of parameters. You can perform statistics. You can do plots. And the other thing that dadi-cli enables is inferring distributions of fitness effects, which aren't so relevant to this year's competition, but maybe in the future. So the really important thing about dadi-cli is that it removes the need for custom Python scripting that using dadi often demanded. So it really makes things a lot easier to use and enables analysis by a much wider part of the community. The other thing dadi-cli gives you as a user is really easy parallelization. So the way that dadi identifies the best fitting sets of parameters is to start many optimization runs from many different sets of parameters. And that's a very, very highly parallelizable process. But in the past, dadi didn't really have built-in facilities for running in a parallel manner. So now with dadi-cli, you can easily use all the cores on whatever machine you're running on. And we can also coordinate between nodes on an HPC cluster or even across nodes within the cloud. So it makes it really easy if you're fitting a complex model to leverage lots and lots of computing power. That won't be so necessary today because we're actually be running a fairly simple model. So in case you're not familiar with the idea of an allele frequency spectrum, let me walk you through it. So we begin with genomic data. In this case, we have 2 samples from individuals from Europe and 1 sample from an individual from East Asia. Now, if we line up those genomes, we'll identify places where there are polymorphisms, where not everyone has the same base. And if we compare with the chimp and outgroup, we can tentatively identify which allele was the ancestral state and which is the new mutation, the derived state. So there's a lot of information in these patterns of mutations. The allele frequency spectrum is a compact summary that preserves certain aspects of that information. And what it really is a fancy histogram. So in the case of 2 populations, it turns out to be a 2-dimensional histogram, which we represent as a matrix. So for example, the red circle mutation is found in 3 haplotypes from our European sample and 0 haplotypes from our East Asian sample. So the 3-0 entry of our matrix gets a 1 in it. And both the blue triangle and the green square mutation are found in
one haplotype from our European sample and one haplotype from our East Asian sample, so the 1-1 entry has a 2 in it, and so forth across the entire genome. So in a real analysis, we might have tens of thousands or even millions of SNPs for which we can accumulate all these allele frequencies. And this isn't a complete summary of the data, because of course we're losing information about linkage disequilibrium and the relationship of mutations with each other along the genome, but it does turn out to be a very useful representation that we can learn a lot from. And so now that we know about dadi-cli and about what an allele frequency spectrum represents, let's return to POSIT and start doing some analysis.
So now we're back at our POSIT cloud environment, and we want to be working in the terminal. And since I took a break and my cloud instance shut back down and suspended, I'm going to reactivate it and set my path again. And if I just run the dadi-cli command, it'll take a second the first time it runs. But what it will pop up with is a brief message telling us, hey, you need to use a subcommand to tell dadi-cli exactly what you want to do. And so the first thing we want to do is generate the frequency spectrum corresponding to our data. So we're going to run dadi-cli GenerateFs. We're going to say we want to analyze the population of wisent. And we're going to reference this pop-info file. And this is a very simple file that I'll show you in just a second that maps sample names to the population they're part of. We tell it which VCF file we want. We tell it how many haplotypes we want our frequency spectrum to represent for each population. In this case, we have a single population of 20 diploid individuals. So we want a frequency spectrum that is 40 units long. We want a polarized spectrum. So we're going to use the information we have about which is the ancestral and which is the derived allele. And lastly, we want to tell dadi-cli what to name the file that's going to come out. So let me return to that pop-info file. You'll see it's very, very simple. It's just a list of sample names followed by the population they're connected to. And in this case, when all the data is from a single population, it's really quite trivial. And here is the frequency spectrum that was generated. So this is really the key line here in the middle, where we see the actual counts at each allele frequency. So we start with 0, which isn't very informative for a single population. And then we have all the one-mers, all the singletons that were in our data, all the doubletons, all the tripletons, and so forth. And so this is the summary of the genomic data that we're going to be fitting models to. So rather than looking at the frequency spectrum this way, we can make a plot pretty simply, where we tell dadi-cli what frequency spectrum we want to plot, and we give it a file name that we want to output to. And this generates a PDF file. And here is our frequency spectrum. So what we're going to want to do is we want to specify some sort of model of the population genetic history and then fit that to our data. So dadi-cli has lots and lots of models built in. You can get a list using the model command, and it's a little bit overwhelming. But for our case, we're going to fit a model we call the growth model. And so this is a model in which at some point in time, the population size starts changing exponentially. It might be growing, it might be declining, but the parameters we're going to infer are the final population size relative to the initial size and the time at which the population size started changing. And so when you do infer our demographic history, which is a relatively complicated command with lots of options. So first, we have to say which frequency spectrum we want to use. That's pretty easy. Then we need to tell dadi-cli the file names it's going to use to save the data, the analysis as it goes. So dadi-cli could potentially generate a lot of different files because if we have lots of different optimization runs, we want to be able to combine that information in a systematic way. And so what we do is we tell dadi-cli what prefix to start our file names with, and then it'll generate sort of the details of what each file is. We're going to have a growth model, and then we need to tell dadi-cli what the upper and lower bounds of our parameters are. Now, you might say the model only has 2 parameters. Why am I putting 3 in the lower bounds and 3 in the upper bounds? And that's because by default, dadi-cli fits a model that assumes there might be some error in identifying what the ancestral state is of each mutation. We call that a misidentification parameter, and that can run from 0 to 0.5 would be just random guessing. And lastly, we're going to use the force-convergence flag. And what that says is that dadi-cli is going to run optimizations from different parameter starting points until it gets a number of them that all give the same best fit set of parameters. And this suggests that we've really found a global optimum rather than some local optimum that any particular run of the algorithm might get stuck in. In this case, we're only going to run 5 optimizations, but in a more complex model, we might need to run many more. And so this will take a few seconds to run. And while that runs, I can describe what we'll be doing next. So what this is going to do is generate a best fits file when it finishes up. And what that does is that's the file that would combine the results of multiple optimizations to really say which are the best parameters that were found across a whole series of optimizations. And then we can use that file to do some plotting and to interpret the analysis, interpret the results of the population genetic model fitting. And so if we watch, what we see is dadi-cli did 5 separate optimizations, and all of those optimizations actually came to very, very similar estimates of the parameters. It turns out this is a pretty easy problem. So we have the likelihood, the new estimate, the time estimate, that proportion of sites that were misidentified, which we inferred 0, which is a good sign because, as I told you, we're giving you very perfect data in this round of GHIST. And lastly, theta, which is a parameter measuring how much total genetic variation is there. If we look at the best fits file, this has basically the duplicate information because in this case, 5 optimizations were enough to get everything we needed to know. If you were running a more complex model that you had to run many more optimizations, you might have thousands of optimization runs and really only want to focus on the best few. So now we can return to our plotting command. But now we have a model. So we can tell dadi-cli that in addition to the frequency spectrum of data, we have a model. And we have some optimized parameters. And dadi-cli will be wise enough to know, oh, in this case, you probably want to compare the output of that model with the data. And so here we get a more complicated plot with two windows two panes where in blue are the data, in red is the model, and in green are the residuals. So the residuals measure the deviations between the model and the data. And you'll see in this case that there's quite, the residuals are small and quite evenly scattered, suggesting that this model fits the data very, very well. So if we think back to what we were asking you for in the challenge, it was a magnitude of the population decline and the time at which that population decline started. So the magnitude is easy to read off here. It's just about 6% was left. The time is a little bit more complicated. And that's because dadi returns the time in these strange units of 2 times the effective population size generations. So we have to infer that ancestral effective population size. And the way we do that is to use theta. So from population genetics theory, theta is equal to 4 times our reference population size, in this case it's the ancestral population size, times the mutation rate, times the total length of the genome that was sequenced. So we've gotten theta from our inference. Mu, I need to sign in again. And if we go back to the wiki and the challenges, for the bottleneck challenge, we gave you a mutation rate and we gave you how much of the genome was sequenced, 100 million base pairs. And so then nref is going to be equal to our theta divided by 4 times our mutation rate, which was 1.26 times 10 to the minus 8th, times the amount of the genome we sequenced, which was 10 to the 8th base pairs. So we get an nref of about 14,135. So now we have exactly the parameters we need to work with to fill in that YAML file. And so, as you'll recall, we can go get our provided YAML file and download it. And it's now sitting on my hard drive. So now that YAML file is sitting on our hard drive, we can edit it in whatever text editor we like. Since I'm on a Mac, I'm just going to use the built-in text editor. And you'll see that I have 2 things I need to fill in. The first is the post-decline fraction, which is pretty easy to read off of the results of our dadi analysis. It's just 0.0615, let's round. The time in generations is a little bit trickier. So Daddy returned a time of 0.025, which doesn't make sense as a time in generations. And that's because Daddy infers times in units of 2 times the reference population size generations. So to convert this time into a number of generations, we first need to infer the reference population size. And we can do that using a bit of population genetics theory. So theta is equal to 4 times the reference population, effective population size, times the mutation rate, times the length of the sequence we're analyzing. So if we can invert this and solve for n or f, it's going to be equal to theta, which in this case is about 71,000, divided by 4 times the mutation rate. So how do we know the mutation rate? So that's something we've told you. Now the mutation rate is 1.26 times 10 to the minus 8th. And we also told you how much sequence data was collected to generate that VCF file. And in this case, it's 100 million or 10 to the 8th base pairs. And so we get a reference population size, effective population size of around 14,000. And so our time in generations is equal to this time in population genetics units times 2 times the effective population size, or roughly 700 generations. So we can go back to our submission file and just type in 700 and save that file. And now we're ready to actually make our submission to Synapse. So we return to our Synapse page, and look, there's a submit button right here, but we're not actually ready to use that. So if we go to hard to participate, we'll see how to submit a file. And the first thing we need to do is to create a Synapse project. So whenever you're working with Synapse, you need to have a place to put your files, and that's in a project. So now we need to create our own project. So we go to this button here and hit the projects, and we create a new project. So I suggest a nice an informative name like GHIST 2024 or something. And we create our project. And we see we have the option to add files. And we can upload a file. And we can just drag and drop. And so now our file is visible on Synapse. And we can see that, yes, it is the version we edited. The submission file is on Synapse. It's pretty easy to actually submit it to the competition. So we'll go back to the competition Synapse space. I always find it easier just to use that link on ghi.st. And if we go to challenges and the bottleneck challenge, we can submit to the GHIST bottleneck challenge. And we need to find the entity we want to submit. So we go to our project that we created, and we only have one file there. And if we select that and scroll down, we can submit it to the challenge and say we are submitting as an individual. So now our file is with the challenge, and the behind the scenes an AWS instance is spinning up to run the leaderboard. So if we go to our leaderboards, ours hasn't shown up quite yet. So it'll be just a few minutes, and then we'll see our results.
A few moments later.
So it only took a minute or two, and I received a couple emails updating me on how my submission had been accepted and that it was being scored and that then it had successfully been scored. And so now you can see my submission here on the leaderboard and the score my submission got. And you can see that I'm a little bit behind our leader right now. So in addition to submitting the file with your results, we also ask you to provide us information about how you got those results. And so we want you to create a write-up. And that is done by editing the wiki that's associated with the project that you created to make your submission. So if we go back to our project, we can see that the front page has a wiki. It's empty right now, and we can edit the project wiki. And we start with a blank slate. That makes it a little bit challenging. But what we can do is visit the template we've created and view the source and just select it all and copy paste it into our wiki. And so you'll see that we ask you to describe your general thinking and approach for each challenge in a brief paragraph and to specify what programs were used and any judgment calls you had to make. So in this case, the author is me, GHIST. I'm associated with the University of Arizona. And I have only submitted so far to the bottleneck challenge. So I can say that I use dadi-cli to analyze these data, assuming an exponential growth/decline model. I estimated the ancestral effective population size inferred value of theta and use that to convert the inferred time in genetic units to generations. And that's probably sufficient for this particular example. And we can add that this was done as part of the GIST workshop, just to have a little bit more information. So now if I save that, you'll see that our wiki is updated. And we would also like to gather your information about any other information you'd like to share us about your experience with the competition. And so that should all be pretty straightforward. One aspect that may not be fully obvious is that for this to work, we need to make our project visible to the outside world. So we can go to Project Tools and edit our project sharing settings and just make it public. And this will allow the organizers of the competition to be able to actually see the front page of our project and see what our description of our methods was. And then we can go back to the submission tutorial and submit our write-up here using this link at the bottom. And so we select the entire project and submit. There's no leaderboard for your write-up, but this notifies the organizers of the competition that your write-up is actually there. And there we have it. We have a submission to the leaderboard, and we have submitted to the Genomic History Inference Strategies Tournament. Hopefully you see that it was pretty easy and that the first challenge was pretty inviting. Things will get more complicated with the subsequent challenge, but I expect that many of you are ready to handle that challenge. And we're really looking forward to getting your submissions and seeing all the different ways that our community can come up with to analyze these data and discover our genomic past. Thank you for your participation, and we look forward to seeing all your entries.